Hello, everyone. All right. Thank you. We're back thank you, Jared. Um, what? Yeah, it's okay. We forgive you. So we're going to do our first and only presentation of the night. For this presentation, I'd like to introduce our speaker. It's me. So without further ado, I'm just going to launch right into this. Tonight, we're going to talk about approaches to reverse engineering .NET applications. And when I say that, I'm going to focus mainly on C# applications, but the same techniques apply to Visual Basic applications, anything that runs on the .NET CLR. We're going to talk about tools, techniques, and countermeasures, so that I'm going to present some stuff, and then you can see if you want to put countermeasures in place. We're going to talk about what you can do to prevent people from reverse engineering your .NET apps. So just real quick, we're going to do why reverse engineering .NET apps. What are the goals? Like, what are you trying to do if you're reverse engineering a .NET app? We're going to talk about server-side .NET apps and client-side .NET apps. And then we're going to talk briefly about modifying .NET applications without the source code and then having them still run. And then we're going to conclude with the anti-reverse engineering techniques. So that's a brief overview. This presentation is not super long, so hopefully I'll just do this and you can go back to talking to people because I'm really not that interesting. But this is my brief introduction to myself. I'm a threat researcher at Aruba Threat Labs. I work for Aruba Networks, Hewlett-Packard Enterprise. I'm really focused on firmware security and embedded Linux devices, particularly in networking appliances. I am a board member of SecDSM. I live in Bondurant, and I moved into security from web development. So my first job was as a C# web developer, and I did that for a few years, and then I kind of slowly moved into security. So hopefully that means I have some authority to talk about .NET applications and not sound like a complete fool. So I wanted to give a brief summary of this presentation before we go through it all. So applications that compile down to bytecode for either .NET or Java. We're not going to talk about Java too much, but a lot of the same techniques apply there if you're interested in Java specifically. But anything that compiles down to a DLL, a jar, a WAR file, or an EXE, there are tools out there that can create a near source code level representation of the program. Another key takeaway from this is there are ways to modify .NET applications without the source code and have them still run. So why would anyone want to do that? We'll go over that, but basically hijacking program control flow to do something an attacker wants it to do that the original authors did not mean for the application to do. The third and final most important takeaway from a blue team perspective, obfuscation of your .NET applications is generally enough of an impediment to deter reverse engineers. So if you take away nothing else from this presentation, just know that obfuscation is usually enough to deter an attacker in terms of reverse engineering your .NET assemblies. All right, so why would anyone want to reverse engineer a server-side application? I'm going to go over the attacker perspective and the software developer perspective. So as an attacker, the most common reason I want to reverse engineer .NET applications is because they contain secrets, like API keys, session tokens, certificates sometimes, private keys even, cryptographic material. A lot of times that's just hard-coded into the application, and as an attacker, I want access to those secrets. The other kind of use case for reverse engineering server-side applications, I, as an attacker, may want to modify your application to do something that benefits me and probably causes a problem for you. So just as a side note, doing this sort of attack, this sort of source modification attack, is possible in .NET using the ILASM and ILDASM tools for the .NET CLR. And if you have Visual Studio installed, you have those tools. Just open up the Visual Studio command prompt, and those will be on the path. You just have to type ILDASM or ILASM. And ILDASM has a nice GUI front into it, so I'll show pictures of it later. But it's really easy to navigate through if you've never opened it before. So from a developer perspective, why would why would a software engineer want to reverse engineer server-side applications? Well, the first reason I see is the source code gets lost to applications, either just because time has gone on so long or there's some horrible catastrophic data failure. Sometimes the source code to applications gets lost, and you may need to make an update to that application, in which case you need to reverse engineer the application to do that, to make those updates. Another common use case I see for developers reverse engineering .NET applications, you may need to integrate with a product, some product that has some sort of strange integration that's not well documented. Maybe the company went out of business and all their documentation is gone. Or maybe they just never provided any documentation to begin with, and you are tasked as a developer to integrate with that product. In that case, you may need to go and reverse engineer that product so you can understand how to integrate with it, how to write code for your application that integrates with the other application that you don't have any documentation for. Another use case, this borderlines on the security aspect, but as a developer, you may want to analyze proprietary code to understand how it works. Like, let's say your competitor has a piece of code that you want to understand how it works. For whatever reason, reverse engineering is generally the only way that you can come to that understanding, by taking what they distribute and reverse engineering it to come to an understanding of what they're doing. Lastly, where kind of development and security intersect. As a developer, it's important to understand what I, as an attacker, what an offensive security attacker can do with your production binaries once they have access to them. So that's where the development and the security intersect. Is like, it's really important for developers to have an understanding of just what can happen from an attack perspective to your production binaries. So just some background on .NET, like for C# files, you have these text files that end in .cs. They're CS extension text files. And those CS files compile down to .dll or .exe files. .dll files are generally what you see in web apps. Like, you load them into IIS, and then IIS does the web app stuff and uses your DLL to power your application. If you're writing like a thick client app or something that runs on a desktop, not a web app, you're going to see the .exe files. That's just your standard, Microsoft application .exe. Now, both these .dll and .exe files, they're based on what's called an MSIL bytecode, missile bytecode for server-side apps. This is the equivalent of Java's JVM bytecode, and the bytecode runs on the CLR, which is the Common Language Runtime, just like Java bytecode runs on the JVM, for comparing to Java, if you're familiar with Java. So when you have this MSIL, intermediate representation, the .NET CLR interprets that into machine instructions, which are then executed on the CPU. The .NET CLR is what actually converts MSIL to machine code and executes that machine code on the processor. The source files are .cs files, and those compile to exe or DLLs, like I just covered. DLLs are more common for web apps. That's what you load into IIS. I kind of went over that just a minute ago. So I want to talk a little bit about the tools that people use to reverse engineer .NET apps. We're going to look at 2 tools for server-side applications and then a couple tools for client-side applications. So the first application I see used most often with .NET reverse engineering is called ILSpy. Now, ILSpy is preferable to many security professionals because it's open source, and it can run on Linux, Mac OS, and Windows. But really what we're concerned about is what it outputs, right? We're concerned about the source code level representation that the tool gives us from the production binaries, from the compiled assemblies. And in that perspective, I consider ILSpy output to be sufficient. It's good enough to be able to read and understand what's going on. Now, if you want to do anything more than understand what's going on, you're going to need probably a different set of tools. But before we go to the next tool, I want to show a screenshot of what ILSpy looks like. It's basically got an assembly explorer that loads all the assemblies in the GAC on the left, and then any assemblies that you load into the tool also on the left, and then the good stuff is what's in yellow here, the source code level representation of the compiled assembly. So it looks kind of like an IDE, like a read-only IDE, and this is what you get. You load your assembly in, you get source code-like representation of the assembly in C# format in this main text window. So let's say running on Mac OS or Linux is not important to you. Let's say open source, being able to audit the source of the disassembler or decompiler is not important to you. There is another tool called Dotpeak. Dotpeak is the JetBrains .NET decompiler. It's free to use. You have to agree to JetBrains license in order to use it, but it does not cost anything. Like I said, it's closed source, so you can't really audit the source code unless you're reverse engineering it. And the main takeaway from Dotpeak is that it can export your assemblies, the source code, as Visual Studio projects. Now, depending on the level of reflection you use in your assemblies that you're trying to load, you may or may not be able to recompile that Visual Studio project without modification. A lot of times I see applications that use a lot of reflection need modification. The output from Dotpeak needs modification in order to recompile. But if you don't use a lot of reflection, then many times you can just take the Visual Studio project that you output from Dotpeak, load it into Visual Studio, and recompile the assembly. And then you can make whatever modifications you need to with a source code level representation of the original assembly. Now, I gave this talk at Iowa.NET user group in August, and one of the attendees mentioned that he had a client approach him once about removing the strong key naming feature of the .NET assembly on an assembly they didn't have the source code to. And he mentioned that this was how they did it. They had to use a decompiler tool to create a representation of the source code, modify that representation so it would recompile, and then recompile it to get named that strong key signing protection that the binary offers. This is a screenshot of Dotpeak. It looks a lot nicer than ILSpy from a GUI perspective. It's a lot easier on the eyes, I think. But it basically has the same layout. You've got your GAC assembly explorer on the left, and you've got your source code representation on the right. If GUI is really important to you, I think that Dotpeak is superior to ILSpy. ILSpy does not have as nice of a GUI as Dotpeak does. But if you're going to be doing this type of work, I highly recommend trying out both. They're both free, so there's no disadvantage to trying out both of them to come to an understanding of which one you prefer as a reverse engineer or software developer doing reverse engineering. So let's talk a little bit about client-side.NET, transitioning from server-side.NET to client-side.NET. Now, where does .NET run on the client? An Xamarin application. So you can actually write Android applications that use Xamarin to execute .NET assemblies in Android. So really what you're doing here is you're extracting the .NET assemblies from the Android app, and then you use the tools we mentioned before, the same tools, Dotpeak and ILSpy, to reverse engineer the assemblies. But the first thing you need to do is extract those assemblies from the APK. So the tool I recommend for this is called JetX GUI. It's a tool that's made specifically for extracting contents from Android applications. And it kind of looks similar to Dotpeak and ILSpy. So you have a tree view on the left of your assemblies, right? And that's just the resource folder, the res folder, and a Android APK. and that res folder contains the the .NET assemblies that are then executed on the Xamarin Platform. So you kind of get a view of what assemblies are in the APK, and then you can use JetX GUI to extract those assemblies from the APK themselves. So you may be able to do this with unzip even. I think APK files are just zip files. But if you're looking for a nice GUI to do it for you, or you're trying to extract like a decompiled version of the Android app, the native Android app, I use JetX GUI. It works great. So another topic that I think is important to talk about is modifying .NET Missile bytecode without the source code. So I'm going to talk about the next few slides how you do this, how you take a .NET assembly and make modifications to it and then let it run and have it do what you need to do as well as what it was originally intended to do. We'll talk about why anyone would want to do this, some examples, the process you have to undergo, which is quite elaborate to do this, and then some of the tooling that helps automate or make this possible. So why would anyone want to do this? From the development perspective, you want to modify an application when the source code is lost. You have to make a big update to your .NET app and you don't have the source code anymore. You have to use this technique I'm going to describe to make your update to the .NET application. From a security perspective, I might want to patch an application to log out sensitive information to the file system. For example, in a server-side context, when a login request, an authentication web request is received on the .NET application, maybe I as an attacker want to log out the username and the password supplied to the login function to the file system. Why would I want to do that? Harvesting credentials, straight up right. If I want to get access to a bunch of your users' passwords, I could go, and I have access to your host, I could go to your database and dump all the hashes, or I could just log out the user's credentials in the clear text when they're being supplied to the application. I can wait 2 weeks and come back and get that text file and have a nice list of all your users with their, their passwords logged out. So that's kind of a server-side example of an attacker making modifications to a .NET application and what can happen. From a client-side perspective, let's say your Xamarin application makes a web request to a legitimate server you host, like it's the server that handles the authentication for your web application. And you get back from that valid web request a session token, right, that identifies subsequent web requests as being from you. And what happens if I've modified that client-side web application, client-side .NET application to send that session token to a third server, an attacker-controlled server that I control? I've essentially stolen your users' valid login sessions at that point, and I can do whatever they can do. So, you could also modify the client-side application to do what we did in the server-side context, log out username and password and send that to a third-party server. But I just want to demonstrate that you can modify these client-side applications to make web requests wherever and send whatever data you want, and that has a lot of security implications for developers. So this is the elaborate process I was mentioning. This is kind of twisty, turny. I'm going to do my best to describe it. If this doesn't make sense, just know this was very difficult to figure out, and it's kind of hard to follow along with. So let's say you have some .NET code you want to inject into a target application. What you do is you take that code and you compile it into a command line application as a function that the main function calls, right? And you write your function so that it accepts the data in the format that it's presented in the application you're targeting. So from our example earlier, username and password, I would write a function that takes a username and a password and does what I want it to do with it. Either write it to the file system or make a web request to some random server where I'm collecting all the passwords. So I take that function, I call it from a command line application, and I compile it. So now I have a command line application that has my function in it, that's being called from the main function, and I have the disassembly for it. So I take that compiled console application and I disassemble it. I take the function that I wrote in the disassembly, and I copy it, right? I remove it to be used somewhere else. And then I take the target application that I wish to inject into, and I disassemble that source code. That's going to be an assembly in .NET. So I take an assembly and I disassemble it. I find where I want to inject my function, and I copy it to that assembly. I copy the function that I'm injecting to that assembly, and then I write some integration code where I pass the username and password fields to my function I wrote, and then I have a disassembly level view of the code as it exists as I want it to work as an attacker. Then I reassemble the disassembly into a compiled assembly, and then I drop that compiled assembly onto the file system for the server-side .NET app. And then you do have to restart IIS if you're targeting a web app. So that can be one thing you look for if you're looking to develop countermeasures for this. Look for a random IIS restart. That could be a sign that someone is dropping an assembly onto your platform that's been modified and that they want to execute then and have it do what they want it to do. So the two things you need to do, the two tools you need to make this happen are the tools I described earlier, ILASM and ILDASM. I provided some links here. If you want the slides afterwards, just reach out, I can get them to you. The important thing to note about ILASM and ILDASM is these tools are made to work together. So you use ILDASM to disassemble an assembly into a text representation that you can then modify. The important thing is that provided you have syntactically correct disassembly, you can then use the ILASM to reassemble the assembly into something that will execute on the CPU. These two tools are available through the Visual Studio command prompt. So that's underneath the Tools menu in Visual Studio. You go to Tools, and then down to Command Line, and then Visual Studio command prompt. Then you can run these programs. I want to show briefly what ILDASM looks like. I loaded in a bouncy castle assembly. And you can see here, I just ran ILDASM from the Visual Studio command prompt. It gave me a nice GUI. I went to File, Open Assembly, and then it gave me this tree view representation of the assembly. The different namespaces within the assembly are presented here in this image. But most importantly, this is just the assembly information. What we want to see is what the disassembly looks like. So this next photo is what the disassembly looks like after you've passed it through ILDASM. This is not, as a .NET developer, I never saw things like this. I never saw .NET disassembly. So if this looks strange to you, no, this is not something that people work with on a regular basis as software engineers. This is really only something you need access to if you're making modifications to an assembly without the source code. You can see here that there's this global CRC field. Pretend that doesn't say global CRC. Pretend that says username. And that's how you start to see how I integrate data fields within an assembly into a function that I have written and call that to do whatever I want it to do. All right, so most importantly, this has been kind of a heavily offensive-related talk. Let's talk about the blue team perspective, because that's probably the most important part of this talk. How do I mitigate this threat? There's two things you can do that don't include obfuscation. We'll go over obfuscation in a minute, but strong name signing. Strong name signing is like Android application signing, using the jar signer tool. So this is a tool provided by .NET or Visual Studio. It's also included on the Visual Studio command prompt. I recommend developers use this to sign their DLLs, to sign their assemblies. The other thing you can do to help mitigate this threat is use read-only file systems for your executable code, right? If it's a read-only file system that's executing your code, I can't go out there and drop a malicious assembly onto your file system and then have it execute, because it's a read-only file system. I can't make modifications to it. And that makes sense in kind of like a cloud environment, right? Where you're deploying these servers ephemerally that can have read-only file systems that execute your application code. And that's one way of protecting against this modified application threat. Let's see. The primary thing, though, if you're really looking to deter people not only from making modifications to your assemblies, but also reverse engineering them to come to an understanding of how they work, is obfuscation. Now, the best tool that I have seen for .NET obfuscation is Dotfuscator. There's a link to it, preemptive.com, products.fuscator. The benefits are it does make code extremely difficult to understand. It makes it difficult for code to modify the code. But the con is that it's usually expensive. Dotfuscator is not free, so you just have to make that trade-off for your organization of the threat of this happening versus the cost of the tool that can help mitigate that threat. The goal of obfuscation is just to make your code as unreadable as possible through reverse engineering tools while still having your code execute and execute performantly. A lot of obfuscation tools like toy obfuscators that people like me make, they have a heavy performance penalty for using them. So a goal of a production-worthy obfuscator is to be performant, to not have more than a 20 or 30% performance impact for your obfuscated code. The last point that I want to make is that obfuscation alone is not sufficient to secure an application. You can't use obfuscation to hide secrets in your source code. So if you have secrets hard-coded into your source code, you should investigate ways to get them out of there. Secrets should not be stored in source code. They should be stored in some sort of secrets manager like HashiCorp Vault, or the AWS has one, a key management service maybe it's called. Secrets belong in a vault or a secrets manager. Compiling them into source code is dangerous. If you liked this presentation and want to go further, there's one book I want to recommend. It's called Manage Code Rootkits. It goes into modifying the .NET CLR itself as an extension to what I've been talking about, which is like modifying .NET applications. So if you want to go and learn how to modify the toString function in the string assembly, like this book will teach you how to do that. It was written in 2014. Some of the information's a little dated at this point, but it's still really good, really valuable read. That's about all I have. So if you have any questions, I can take that now, or we can just shut down and go back to socialization. Are there any questions? Anything anyone wants to ask? Are you laughing at me? Okay. Okay, so the CTF is going to end at 6 p.m. tomorrow. So if you're doing the CTF, you have tonight and tomorrow to work on it. We usually do, SecDSM usually does a Friday night hangout in our Slack channel. You can join our Slack channel at secdsm.org. We highly recommend you do that. And then you can join in on this Friday night conversation with us on Slack and tell us how you solve the CTF. If you are the winner of the CTF, we'll get you a prize of some sort. So maybe that will encourage you to do it. All right, that's all I got. Thanks, guys.